Suppose that we have two unit vectors in 3 dimensions, and the directions or the axes around which these two unit vectors may rotate. And we want to rotate them in such a way as to make them parallel, more or less like this. How can we calculate the angles through which we must rotate each vector? Well, one of the things that we know from our knowledge of vectors is that if two vectors have the same length, which of course any two unit vectors do, and the same direction, they are by definition the same vector. So let's use that in order to take a little bit different look at this. Here we have the two cones of rotation joined at their points, and the idea here is that when we rotate them, the two given vectors u1 and u2 together, they become the same vector by definition. So the rotated vector u1, which this denotes, in this position is equal to the rotated vector u2. So this shows us that there are only two solutions here unless the cones are disjoint or touch in only one line. And also, if we look at this, we can see that, well, we have to get u2 over to here. So it doesn't matter where u1 is. Theta 2, this angle of rotation for u2, is independent of the position of u1. Similarly, theta 1 is independent of the position of u2. So that's a big hint. And we're going to use it in the context of geometric algebra. And in geometric algebra, instead of dealing with axes of rotation, we usually deal with planes of rotation, and those planes of rotation are defined by their unit bivectors. So here we have the two unit bivectors for each cone, or each axis of rotation. What we will see then in this video is an introduction to this paper that is linked in the video description. And what we'll see here is just kind of a synopsis of it, or the high points. We'll see the benefits of exploring problems via interactive constructions like GeoGebra. We'll also see a version of the geometric algebra rotation formula that makes a problem simple. And we will see how to use geometric algebra products to eliminate variables in simultaneous equations. And throughout this video, I will also be linking previous videos up here for background and more details. So let's begin by reviewing the geometric algebra rotation formula and its transformation. Here's the transformed version that we'll be using. And the rotated vector w prime is equal to the vector sum of w's perpendicular component, or component perpendicular to the unit bivector, plus the cosine of the angle of rotation times this projection of w, plus the sine of the angle of rotation times this vector, which is the 90-degree rotation of the projection of w in the sense of rotation of the unit bivector. It's important to note that both of these red things here are single vectors. So our first step is to express the rotations of our two given vectors, u1 and u2, according to this plan here, according to this transformation. And I've presented the previous figure just for reference. So you can read these yourselves if you want to stop the video for a moment, but I'll just continue on here. Step 1 then, here are the results from the previous slide. Step 1 is to equate these two things. Now at first sight that looks like a really dumb idea, because we end up having cosines and sines of both angles in a single equation, and now what on earth can we do? Well, let's recall again that u1 perpendicular and these two things are all perpendicular to each other, and the same goes for u2. u2 perpendicular is perpendicular to these two beasts. So that's a big hint. And also we go back to the fact that The angles of rotation are independent of each other and of the current positions. Well, theta 2 is independent of the current position of u1, and theta 1 is independent of the current position of u2. Those are big hints. So there should be a way of knocking out the two theta 2 terms here completely. And how might we do that? Well, again, these three things are all perpendicular to each other. So what do? Well, we dot both sides with u2 perpendicular. And the dot product, inner product, distributes over a sum. So here we get u2 perpendicular dotted with itself, u2 perpendicular dotted with something that's perpendicular to itself here, and u2 perpendicular dotted with another thing that's perpendicular to itself here. So u2 perpendicular with this is 0, u2 perpendicular dotted with this is 0, and the right-hand side reduces down to just the square of u2 perpendicular. So now our next step here is to transform that into a standard trig equation. This is the result from the previous slide, and if we work that around a bit, we end up with this. We have a known scalar times cosine theta 1 plus a known scalar times sine theta 1 equal to a third known scalar. Now we can transform this using standard trigonometric and GA identities. This is the result from the previous slide. We can transform that into, well, this is the cosine of the difference of two angles here. And alpha 1, cosine alpha 1 rather, is this. Cosine alpha or sine alpha 1 is this. And the details are presented in the paper that I mentioned earlier and which is linked in the description. So that is really the end of all the geometric algebra. The rest is just simple trig. So the takeaways from this presentation are, first of all, the benefits of using interactive constructions like GeoGebra. That gave us some big hints that helped us a lot. Also, we should consider the different variations of the rotation formula in GA before diving into a problem. For example, I could get nowhere using the exponential formula for the rotation in this problem, but using the transformed version that I showed earlier, it ended up being simple. Likewise, we should consider the various implications of the given data and of what is required. For example, when we found out that u prime 1, or the rotations of u1 and u2, had to be equal to each other, well, that meant that their exterior product would be 0. Well, when I tried using that, I got nowhere. But setting the two equal to each other, well, it turned out to be simple. And as a last takeaway, we should always look for ways to eliminate variables using geometric algebra products. I hope that you'll consider joining the LinkedIn group Pre-University Geometric Algebra, which is dedicated to preparing instructional materials for GA. And please check also the various links in the description. Thank you for your time.